Hi, my name is Ken Lasseson. I have created a website called microbiomeprescription.com, and this is part of a series of lessons dealing with the microbiome. The purpose is to educate both um, patients as well as MDs and researchers on the microbiome, mainly because things have changed rapidly over the last 10 years, and there's some interesting complexity to it. So just gives you my slant on it after having worked with it for a couple of years now. I'm by training, I'm a statistician, a data scientist, also a developer, which is why I have been able to produce the website very easily or relatively easily, lots of hours, but I know what each component needs to do. So in this section, I'm going to be looking at identifying issues by the bacteria alone. This is a logical first step. When I first started, this was the direction I originally went into, and as I dug deeper, I discovered some interesting twists, and this basically describes what those twists are and my opinion on them. And you can come to your own opinion on the issues after seeing the evidence, keyword evidence. Okay, so let's go in and do a quick recap of the lessons. The first one was lesson which is already up online is who am I and what's my world data perspective, which gives you my history and how I got interested in this area. This one is looking at how to identify bad apples or good apples or too many apples in the barrel, and part of something which I refer to as the randomness challenge. One time life was very simple with the microbiome. There's only a few dozen species involved, and therefore your choices were simple. And often the patterns given those choices was relatively restricted. Now we have literally tens of thousands of bacteria which could come into play, and we now become a bit random in which bacteria we pay attention to. So that's part of the randomness challenge. Then I'll be going and looking at PubMed studies. We're picking bad and missing apples. PubMed study is close to what happened for me to become interested in the subject because there was a study showing a particular shift. I used the information on that shift to have a eureka moment. Then we'll go on to using symptoms to pick bad and missing apples. And in that case, it is saying, look, diagnoses are fine, but generally diagnoses are broad paintings of, in some cases, 20 or 30 different symptoms. If we go back down all the way to each individual symptom, guess what? Data becomes clearer. Bundling so many symptoms into one sometimes causes significance to disappear. Then I'll go and take a look at end products, which is trying to view the bacteria in a different way. Instead of saying this bacteria or that bacteria, say, okay, what do the bacteria produce? I'm high in folate or I'm low in folate? Well, that may be caused because I'm high or I'm low in the bacteria that produces folate. So it's sort of working backwards, saying, okay, this is the result. I can measure those things in my lab. What causes it? Note, we're talking about not how to fix it, but giving you folate supplements. What we're trying to do is go back to the root cause, having the wrong bacteria mixture, and we're going to strive to correct the bacteria mixture. So it's doing root cause analysis and root cause treatment. An interesting twist of focus. Then we move on to enzymes, and believe it or not, most people know a few of the enzymes involved with the gut. Well, there's over 1,600 different enzymes involved with the bacteria in the human gut, and we have written software to identify which enzymes are being overproduced and underproduced, and what we can do about them. Then we look at another part of the Kyoto enzyme database, which is the moleculars, And we also will apply that. Again, all of these are different ways of taking the bacteria and seeing what do the bacteria do or cause, and can we identify from what they cause oddities of behavior or high or low amounts which probably shouldn't be there, and thereby backtrack to the bacteria that should do it. Everything is focused on trying to identify the bacteria that we need to modify. Then we go to sorting apples. In other words, which bacteria do we go for or don't go for, ignore it, do ignore, etc. And then develop a recipe for correcting the ratios of bacteria or suppressing or encouraging other bacteria. And last is looking at future perspectives in terms of the microbiome. So with that much for overview, let's get into things. Many existing professional diagnostic tests will often report the same thing, be it for bacteria or for other things, and they all tend to produce something very similar. I'm not going to comment about the other test. What I am going to comment is about the microbiome, because I have some hard data I can show you which illustrates the problems. Here we have an example from the biome tests, and we see that the lab returns the numbers. I have no arguments with the numbers probably being correct. They then give a range of what they expect to see, and whether or not your values are high or low. It sounds nice conceptually. It's basically similar to making a test for some sort of blood metabolites like your folate levels, but going and correcting it to the levels they are suggesting too frequently produce no desirable results. I enclose a comment on screen from somebody who I talked to yesterday, and their comment was they used the oats test, which is the organic acid test, and they got things not much better, but for this child with autism there was no change. Approaching it a different way through enzymes and getting suggestions that way, the person saw changes within 2 days. So the problem is selecting what to change and what the consequences are. Okay, let's go on and let's look at how lab calculates results. The cookbook for labs is almost identical everywhere for everything. Unfortunately, when they take their standard recipe and apply it to the microbiome, they miss something very critical. The usual way is you take a sample of healthy people. Often they are not sex, race, age, balance, or whatever. They are, oh, we need 120 people, we need 200 people who are, quote, healthy, whatever that means, and we'll use that to establish our lab's baseline. And they will be from the local area, so that they would be sort of what you expect. Now, from that, we calculate what's called the average and the standard deviation. Average in stats speak is called a mean. Standard deviation is sort of how wide, the plus or minus from what the mean most values are. Okay, now a couple of problems happen. First of all, often the numbers can be as low as just 40 people. Part of it is simply the cost of running so many free tests. Second, often the people may be recruited from, for example, university campus. So you have a strong age bias in terms of the people there. There is no regulation forcing them to do anything. It's suggestions that goes out from the industry as to what they should be doing. They are not per se enforced, or they are self-enforced, which means that, well, whatever somebody decides upon to be good enough is good enough, and you won't find out exactly what they're doing. Okay, let's go on and get back to dealing with the average and standard deviation, or the standard deviation. At the bottom right here, we see what's called a Gaussian distribution, a bell curve, a normal distribution, many names with the same shape. And what happens is the mean is the average value. If it's a Gaussian one, then we should have the mean right in the middle of the curve. One standard deviation is a computation that says that, okay, 68% should be plus or minus this particular value. If you take it to 2, you get 95% of all the values captured. If you take it to 3, you get 99.7% value. But this is what is a normal distribution. If the data matches it, you're good. You're absolutely good. If it doesn't match it, you have a slight problem. And the problem is that if it doesn't match it, then the size of the sample you need could be 10 times more. That means a lot more bucks. And one of the biggest problems is you don't have a statistician on staff at most labs. Why? Well, first of all, there's a big demand for them. But from whom? Google, Amazon. Statisticians are basically nowadays mostly known as data scientists, and they do machine learning, they do forecasting of what you're going to buy next on Amazon, or what you're going to order next at Starbucks. Again, it's all basically numbers grinding, and generally those people can afford to pay a lot more than most commercial labs. I mean, often a good statistician's salary would be far more than what the CEO of a lab salary is. And sometimes that's true even for starting salary. So the problem is the labs don't have the skills to really do a good job of calculating things, and they make the assumption for simplicity or to save money of everything being a normal distribution, and that is an interesting assumption. It is a very easy one to test if we get the raw data. The simplest test is really easy. The median, which is the 50th percentile, half the values are below it, half the values are above it, should be what the mean is. They should be identical, same value, or extremely close. We also have a third measurement, which is called the mode, the most common value, which is, if you take a look here, if you broke it into chunks, the most common value should be right, should include both the mean and the standard deviation, the mean and the median, and if all three of them line up, then you basically pass your first level of test for a normal distribution. If they don't line up, you don't have a normal distribution, and you can't use standard deviations legitimately to calculate what the suitable ranges are. Statisticians can use advanced tests on the data, like the Kolmogorov-Smirnov test, but they require the actual data to perform it. If the lab doesn't present the data or make it available, I can't calculate whether or not it's a normal distribution or not. We can eyeball the chart, but again, that requires the lab to make their data available, and also their data on how they determine or how they pick the sample to see whether or not the samples are appropriate for you. Usually the problem here is getting data from the labs, and they generally don't want to do so because sometimes they know that their data or their sampling criteria is crappy. So they need to protect their reputation and keep business. So that's the beginning of the issue. Okay, let's go and look at some real examples of microbiome reports. That's my concern, my focus. Here is an example of a biome gut report. They don't give a range. They give a nice little pretty diagram and put a dot on a diagram. It gives you numeric values, but you have no idea what the ranges are. Now, when I look at it, I looked at the second one and went, wait a second. The value is 0. Here it is, sitting there nicely, except for one problem. You have just range of values to the left, values below 0, which are in the normal range. How in the world do you have a negative bacteria count? That is a rather glaring mistake and sort of casts everything in doubt. they don't tell us what the values are, and they indicate some abnormalities in their presentation of the data. That means I get real suspicious about anything coming from this lab because basically they haven't even done a reasonable technical review of the data they give to customers. Let's go on and take a look at a few more. The top one is GI map, which is very common. It's what I showed earlier. Again, it shows the edges of the ranges they are using, but doesn't give you the mean or average. If they gave a mean and average and that value is right in the middle, we could surmise that they are using a bell curve and that middle value and the deviation is all being done by standard deviation. Very standard methodology for calculating ranges. Now, we also, in that case, we have some interesting scenarios because if you calculate it for that range and we go down to another lab like BioVest here, you will see the range is below a certain value. And below a certain value means that they at least did the right thing. They may have calculated the average on 2 standard deviation, and when you subtract it, the value went below 0. So they stopped it at 0. But that actually ends up a side problem because high values are no longer in the top 2.5%. They may well be in the top 5%. So you could end up with false positives for having high values. GI effect is another one, which again, popular. They do a reasonably good job. They sort of have the gradations here. But the problem is, once you go beyond a certain point, you just put up a marker there, and this marker isn't the highest value possible, or seeing elsewhere is simply, oh, you're out of range. So you don't have a relative scale of how far out of range you are. You just have a out of range, and you have a set of values which you probably could assume somewhere it's the range of the green values, but we don't know exactly where it is. We don't know unless we happen to have a value right close to the green where the range values and your active values are sitting. Again, all of this is information which is less than ideal to make a good decision. Let's go over and see what is in reality. Fortunately, I have had many people upload the microbiome sites from a multitude of labs, and from their uploaded sites, I have the raw data. I can see what type of numbers actually show up. And what I see is it ain't a Gaussian, it ain't a normal distribution. Remember, here we have percentile. 50th percentile is the median, 50% above, 50% are low. And then we have the average, which should be at the same value. Wait a minute, the average is high. Basically, 72% of the people have below average and 28% have above average. Most people have trouble start saying, wait a minute, that's not what an average is supposed to mean. Correct, it's not. Average, most people expect to be a bell curve. It's not. If you take a look at the third measurement, which is the mode, the most common one, if you break it down into values of 1,000, we find the mode is sitting from 0 to 37th percentile. So the mode is way off to one side, the average is way off to the other side, and the percentile is where it always will be in the middle. So the bottom value is 33 out of a million, top value is 110,000 out of a million. That's a big range. And the ratio between top and bottom is 300,000%. Ooh, dry. So we have that as a interesting problem, as in how in the world are they determining ranges? Basically, minimum lab requirement I would propose for a respectable ethical lab would be to publish the distribution charts and explain the rationale for each range, as well as how in the world they obtain their reference sample. Key information should be open data. Keyword open data. Should be available, should be able to be pulled down into R, which is a common statistical package, for anybody who's interested to do analysis and evaluation of their data they use for reference. Open data is something I believe strongly in, and all my data is indeed open. Okay, now that we have numbers and we have a distribution, we can actually go and view the data on percentile. And on my site, my goal is to give more reliable data with open data and be able to explain why. For myself, I show a hierarchy, which is shown here, and hierarchy can be thought of as looking at people in a city. The bottom level, often the species, sometimes the strain, is talking about those who live on the street. Next level up is the neighborhood. Next level up could be a precinct of the city. Then we have the city itself, we have the county, and then we could have the state. So we have a hierarchy in terms of people, and we have the same type of hierarchy in terms of the microbiome. And with that, we have the ability to see relative to other people where your values are. Are you typical what other people have or not? If you are lower than other people, it'll be yellow. If you're higher, you'll be orange going to red, depending how high you are. But there's some gotchas here. One is how many samples report that. Bacteria, people don't have the same identical set of bacteria always. Bacteria can often replace other bacteria in terms of the function. So the result is, oh, you don't have just bacteria, but you have that bacteria, and it produces almost all the same function. So the result is, for some reason, you may have more of that one, and less or none of the other one, or the reverse. So there is substitution happening, which of course makes things a bit more complicated because it's not a standard performa set of bacteria that every single person has. It is unique for yourself. But that means when you go through, if you see something like here, okay, everybody has it, so these range will probably be applied. When you hit down to something like here, only 6 people have this particular bacteria in 1,300 different people. Is it important or not? It's low, so you have less than the other 6 people, but is it a disease-causing one? Is it significant, or is it just no? It's just random people that happens to have shown up. We don't know, and that's part of the problem. We know nothing explicitly by the name of the bacteria, whether or not it's good or bad. And we have another one here, and we have high. And again, we high, but it's only 124 people. And your count is 110, which makes for the higher end of people who have it. Is this associated with a particular medical conditions or not? We don't know. For a few of them, like over here on the left side, you will see that we have high number of people reporting it, and all values are high in terms of numbers, and we're high in terms of percentile, which means that those are likely going to be significant simply because they're unusual. How and what they cause, we don't know. All we know is they are suspect. They may be innocent, but they are suspects to be investigated. So, going onwards from here, when you, on this prior chart, click on one of the bacteria, you will automatically be taken to a page that gives you a whole bunch of more information for each and every one of the bacteria. You will see the distribution chart, and usually the charts are are presented with a log value, and that's because usually the normal range should be almost a straight line here. When the line starts dipping suddenly or going up suddenly, those are where you are having probably a abnormal values. So here we have 15th percentile is where the lowest 15th percentile are people who are probably suspect, and up here we have it's pretty high before we turn up, so we have probably the top 2 percentile. Again, we generally find that there is a pretty flat straight line. It's when we have the turning up or turning down we have a concern. In this case, we have what the average is shown on screen. The mean is the 50th percentile, and the actual value from the sample is plotted on the screen so you can make a better judgment. Is this a viable suspect that you should pay attention to? Is this something that perhaps you should change? We also find on the page, we find out what end products it produces. And we also have a link to a bunch of more technical pages or more informational pages to provide you with more information. These are almost all going to third-party sources. So you can go and check up on the National Institute of Health Library and get information from there. And then from Published Science, we have assembled what conditions have reported statistically significant shifts. Some cases, it reports that if you have this particular cancer, you often is seen with high amount of this particular bacteria. If you have inflammatory bowel disease, it's typically seen with low amount of this bacteria. Diabetes, high amount of this bacteria. So it will give you some insight whether or not there are medical conditions associated with it. If you happen to have one of these medical conditions, you're probably going to be even more suspicious of this particular bacteria of being something you may want to look at modifying. So let's go on from here. And let's take a look at one particular bacteria for purposes of illustration. I have a quote here. And parts of the world, 60% of the population, 60% of people's gut is one of this bacteria. And down below, I plotted from our sample, 60% is here. Oops, guess what? 97% of people in our samples don't have that much of that bacteria. The average is high, even higher than the last one, is almost 88%. Your value is way down to 30%. But look, we have a horrendously big stretch where there's practically none of this bacteria. Okay, we have the problem of interpretation and what to do with it. Basically, it becomes a messy problem. What I have on the right is a list of articles which looks at some aspect. First of all, from this year's Nature, The Hunt for a Healthy Microbiome, the magic grail of what your microbiome should look like. It's like the Holy Grail in reality. Something you look for, but you never find, and it's actually a futile quest. We then look at racial differences in just a mouth bacteria, which will impact the gut bacteria. We look at changes in diet between children in one part of the world and another part. We look at lifestyle, how much exercise you have impacts the gut bacteria. And then geography, longitude and latitude actually does make a difference in, latitude definitely, distance from the equator makes a significant difference for some bacteria. And let's go on. Bottom line, if you're looking only at bacteria, is you don't know if this bacteria is a friend or foe, whether or not high values mean something to you or not. High values may be a good thing for you or it may be a bad thing for you. Sometimes depend on what medical conditions you have. We don't know which bacteria is just noise and which one is significant. if the bacteria happen to be one associated with, let's say, Lyme disease or with a rickettsia infection, we may know what to do with it. But that's only because we have association of bacteria to some medical condition that we are aware of. Without that association, we cannot pass judgment. We do have some health authorities advocating certain ranges for some bacteria. This is good and bad. Usually, these ranges are gleaned from practice experience. That is, this person has seen hundreds and hundreds of people and have come to the conclusion that this range of value for the people he sees in his practice is where he wants to put people. Trial and error. Again, it's his practice, wherever his practice is, and the type of people he comes and sees. Doesn't necessarily mean it applies to you, especially if he's on the other side of the world and happens to be, let's say, a vegetarian, or half of his people are vegetarians. Then you may have a problem. Usually, these levels are done bacteria by bacteria, and a relatively small number. Often the recommendation on blinker to one bacteria, and generally it's bacteria which are very common across a large number of people. And as I pointed out before, some bacteria in some populations won't show up at all. Oh, you have zero of this one. The person could get quite excited and say, you need to really get it. The need to get it is hard to really justify because there are so many factors that determines if you have any or if you should have any. And most of the time, these recommendations do not consider interaction or substitutions of other bacteria performing the same functions. This is an area which I should frankly state that beliefs run hot here. Internet beliefs on what you should have for your bacterial numbers is strong, and a lot of people are very, very passionate for it. The science generally runs thin for their suggestions, sometimes extremely thin. Most of the time, there's no active consideration for known factors. They're particularly DNA to genetic inheritance. Whether the person being breastfed or bottle feed makes an impact. What gender they are, their diet, latitude, distance from the equator, how old they are, because as we age, our microbiome changes. Particularly from birth until about 16, there are dramatic changes in microbiome. Things are in no way similar to an adult's microbiome, just range. As you get older, we find that long-lived people have a different microbiome than shorter-lived people, which is interesting, as in the microbiome seems to have an effect on longevity, or that people with the DNA to live long has a microbiome which reflects their DNA, because DNA and microbiome are linked together. The amount and the type of exercise, especially in today's work-at-home environment and people not getting out for exercises, gyms are closed, etc., that impacts the microbiome. The concept of having a magical pattern of bacteria to do is very simple, it's very popular. It means you don't have to deal with complexities or working beyond your cognitive capacity. It's nice and simple, easy to grasp. The numbers they propose work for some, but not for others. Percentage works for them, hard to say. Generally, people are successful selling their ratio if they get 45 or 50% reporting positive results, sometimes even less. It doesn't take a high percentage of people finding it help them to have it being sold as gospel across the internet, especially if there are no studies being done of what they're advocating to demonstrate whether or not it really helps people. 30-40%, that's all it takes to sell an idea as being the definitive answer. It's a recipe book, and my best analogy is you got this as a recipe. Take some protein, wrap it in some grain mixed with some liquid, add it in leaves from a tree, put it on some heat, and voila. Well, you could end up with a nice meat pie, or you could end up with food poisoning. What's the protein? The protein could be soy, it could be fish, etc. What's the grain? It could be rye, it could be wheat, it could be quinoa, it could be some other things. What's the liquid? Water, milk, wine, turpentine. Add in some leaves from a tree, poison oak leaves, oregano leaves, etc. The recipe is often very vague and oftentimes produce a nice meat pie, other times make somebody horribly sick. So that's part of the challenge, is that there's a lot of complexities and we need to be able to reduce the randomness of where we're going. Now, having a magic recipe of numbers to shoot for, to me, is old school. At one time, this was the state of the art. No disputing that. At one time, it was the best you could have done. And in that time, during the only thing we knew about was bacteria that we could culture in a petri dish, in an open air petri dish exposed to oxygen. Many bacteria have zero tolerance for oxygen, which means that basically they did not exist. We couldn't see them, we couldn't measure them, we couldn't grow them, they don't exist. That suddenly cuts the number of bacteria to consider down to a very small number. Doesn't mean you don't have lots of other bacteria, but it means the ones which we could measure was very small. And it became pattern matching to the limit of ability to test. We have since changed dramatically since that time. Knowledge and complexity have exploded. Below is a chart of the number of microbiome studies from PubMed by year. And as you can see where we are in 2010, oh, not that many back up to then, and then we have the numbers since then. Most of the medical professionals you deal with probably completed their university education and classes in 2010 and before. Guess what? Unless they have a strong interest, they would probably be ignorant about all of the studies here. Hundreds and hundreds and hundreds of studies, and they will not know about them or what the consequences of them are. They are going to be working on old school knowledge, which is unfortunate, but it's the nature of the knowledge revolution. Okay, at this point of time, I'm going to switch over to the website to walk you through some things. Alright, this is the website, Microbiome Prescription. If you have done a microbiome sample from one of many firms, you can upload it here. Here are the names of the firms which uploads are supported from. With that is the number of bacteria they report on average. Highest number I've seen so far and lowest number I've seen. So, and for upload, it's pretty simple. You go and click on the one you want to upload. You choose the file. That's me, never mind. And you upload it and it adds to the database. It will send you an email with a link to log in with, although you will be automatically logged in with restricted privileges just from doing the upload. If you don't have one but want to experiment, bottom sites here have a demo login, and it's a demo login gives you a sample so you can explore what they report on it, but you can also go back and see what I would report on the same data. Okay, so I'm going to log in with the BiomeSite demo user, which checks us in, and we have a sample which the person has uploaded, more videos by you know who, and it gives you information as to when the sample date is, what's the source of the software that did look at your data, information about who you are. The signature is a way of identifying duplicate samples. Over here we have the bacteria. Taxonomy is the fancy name for the bacteria. It says we have identified 493 different bacteria. Of those, 12 we only see in about 1% of the samples, 22 and 2%, etc. 236 are seen only in 16% of the samples. Just isn't that useful when you have only one sample? If you have two samples, it can be informative to see how those things change. Now, we have a whole bunch of drop downs, which gives you choices to do lots of things to do here for medical conditions, change your microbiome, symptoms, timelines. So it gives you a richness of ways of exploring your data. But we're going to go into sample visualization to my biome view, which is what we actually saw a bit earlier. And when we click that, it will take us to a page. And then it will go and load the data up. And what we have here is the data, which is similar to what we saw. We have the same thing. We have the number of samples, which we have for the particular bacteria, what your count is, the name of the bacteria, etc. And again, remember that a low number here means it's rare, doesn't necessarily mean it's guilty. It just means that it's an unusual face to see in a crowd. It's sort of, okay, this person isn't usually there with most people. We may want to pay attention to it. He could be 100% innocent or 100% guilty. It's hard, we don't know. Wait, but if you go and click on, let's go down here and let's take, actually I'm going to go down to the bottom. As you see, there's a large number of them going there, and just go to scan up and down. Yes, that's what I was looking for, these which were high. And what I'm going to do is I'm going to go and click on one of them. It will take me to a new page which gives me information about it. The first thing you notice is it gives other names. This bacteria, through the last 100 years, you can see some of the dates there, has been known by many different names, which often makes fun for reading papers, because sometimes the older names are used in the paper, which means you have to figure out what's the current name for this bacteria if you want to use any information in that paper. And we have here, we have information about how often this bacteria is reported. For example, American gut, it's never reported on. The other labs, it's very commonly reported. We see what end products, generally vitamins, it produces. We have other technical information. And we now have the chart, so you can see where your value is, what the average value is, 50th percentile. You can see where the curve goes up or down. If you click up here, you can change how you're viewing the same data. You can do value per million, in which case you see this whopping big explosion of values. Or you can change it by percentage, and we see that it goes from 0 up to highest value by 44%. Majority of people are 5% or less. You happen to be sitting here at around 3%, which means 92% of people have less than you and 7% have more than you. So that gives us information about this one particular bacteria. I'll flip over and we can go over and take a look at some technical information. So here we have the beginning of pages upon pages of technical information. You can see it has a ton of links all to this one bacteria, which again can get saturating. Let's not go into that at the moment. It becomes, it's a good thing to do a PhD in. Okay, so let's go back to where we were. And if you go back up here, you can see some other sample visualization. If I click here, I can take a look at, say, okay, I want to look at the information in terms of pie chart. And this is by taxonomy rank. Think of it as in government level. The column is about the highest as in countries. If you go down to class, you're down at a roughly state level. You can go down to smaller levels and find out exactly who is there by neighborhoods. For example, ethnic population in different neighborhoods. And you can go down to species, which will show you at a very low level where things are massively done in terms of the there. Notice we have an unknown, 40% unknown. This is not unexpected because we are still identifying bacteria. We have over 1 million bacteria types identified, and we're working on the 2nd million, and it takes time to catch up, not only to catch up in terms of naming them, but being able to identify them. And then over here we have one particular one which is 18%, other ones 17%. Whether or not that is too much or too few is a subjective question, which there's a variety of opinion on. We can also go over to a more sophisticated chart, the chrono chart, which basically works from the country to state to county to city to neighborhood, etc. So you can go up and down using this chart to whatever point of time you're interested in. Again, it's just a visualization of the data that's available. And we now want to go over and take a look at one more thing which was mentioned, which is, first of all, it's a health analysis, which is trying to get some sort of general map to evaluate what your microbiome. And the dominant presentation comes from a chap in Tasmania, which is off the coast of Australia. And he has some strong recommendation. He is well known. I've met him. I've talked to him. I like him. His numbers are good for what they are, but they are not perfect. And it will tell you what his range is, your value, and whether or not it matches his definition of what an ideal number should be. And up above, you actually even have some tempted predictions based on the number of matches you have of your shifts to shifts reported in medical literature. This is very experimental. It's probably 90% of the time it's wrong, 10% of the time you may be lucky, but it just simply raises questions of things that perhaps you should just talk to your doctor about, checking to make sure that's not the case. Sometimes the microbiome will show things up before it becomes a medically determined conditions. In other words, early spotting. And down the bottom are a variety of bacteria which are assumed to be unhealthy by one or another authority. Again, these are general conclusions, and for example, here we have what we were looking at, and what we find is that it's associated with high blood pressure, high fat content, and high body mass index, better known as being obese, which means that if this person happens to be obese, this bacteria is probably a contributing factor or consequence. We don't know which comes first, the chicken or the egg, but it will give you some idea. And if you are interested in changing it, again, it's straightforward. Goes over to the page that gives you the information, the distribution, but then we end up having more tables underneath it. And what is particularly of interest, which I want to show, is we have a table which shows what increases or decreases it from studies published on PubMed, the National Institute of health library, and we have, well, we have 1,200 items listed. If you type the word herbs, you find out which herbs will increase or decrease it. There's only one herb that will decrease it. Oh, my favorite, caffeine. Yes. And we can also try searching for things like spice, and we find out that everything or increases it, not what we want. We could type in the word food. If we look at food, we see tea decreases. Wait a minute, caffeine decreases. I wonder if caffeine is in tea. Actually, it is. We have also things like barley, which means that barley porridge probably should be a good start for breakfast now if you wanted to take off some pounds. Or berberine, which is a supplement. You can also go in and type in things like vitamin, and you find out that some vitamin decreases, some increases it. You can go over and click on this to sort things in order. So you can see vitamin A, folate, and zinc will increase this particular bacteria, and this bacteria being high implies being overweight. So we have a little bit of fun there, and basically you can go in and do some mixing and matching, or you can get rid of all of this and wander through everything. We have a lot of prescription drugs listed because that information happened to be reasonably easily accessible and extractable. So basically in there, some cases, if you are doing a prescription drug and you are obese, you may want to see whether or not that drug actually increases it. Does it contribute you to being overweight or not? So again, it's information. Doesn't give you the answer, but it enables you to make a more informed decision. Okay, I think I've talked enough for the moment. So let's get this up online.